In this lecture, we are going to start with chapter 10, which deals with hashing. It's a very important concept. And in this first lecture, we will just discuss the idea of hashing, why it's useful, and some basic hashing functions. So in course 212 and in general in your other course subjects, you must have encountered a whole bunch of different data structures up till now. So this table just summarizes the efficiency of the various operations of the data structures that we have discussed in this course, for example. And BST refers to binary search tree. B-trees you all know and love, skip lists, hopefully some of you remember. So if you look at the operations generally, it would seem that the search operation is really the hardest of them all. No matter if you consider the average case or the worst case, and no matter how smart and complicated your data structure is, even for B trees, the best we can really hope for in the average case is logarithmic efficiency. So worst case is generally n when you have to search the entire data structure, and log n is a little bit better, but still we might at this point pause and ask ourselves, is logarithmic efficiency that we get on searching a data structure sufficient? So if you have a really large database, let's say you have 1 million students and you want to search for that particular student in the table of 1 million students. If I take a log of 1 million, is that going to be acceptable waiting time for the user to search the database, or will it actually still be too long? Because obviously a logarithm of 1 million, it's not exactly going to be a small number. So logarithmic efficiency is better than linear efficiency, is better than big O of n, but regardless, you end up with long waiting times if n becomes very large. So we kind of hit a wall here. It seems that we cannot do better than log n. Doesn't mean we're stuck and we just cannot deal with huge data structures. Well, fortunately, there is a solution that is ingenious and brilliant and works perfectly and scales very well, even to very large sets of data. So what we are going to talk about today is a data structure that basically allows you to link a given object key with a given index in that database table. So what we want is we want to design a function that, given an object key, unique identifier, so for the student that would be the unique student number, for example, just by somehow mathematically analyzing the student number, it would immediately tell you, without having searched the data structure at all, it will immediately tell you to which cell in the table, to which location in the table you must go. So what is this magical function? How do we make this work in practice? Let's talk about hash functions. So the basic idea behind hash functions is that we want to create this key index table, and we want the index of every single key to be determined by the key itself, by the combination of the key and the hash function. So the hash function is essentially a deterministic mathematical method of computing the index in the table for any given key. So let's say I have a table, it's this thing on the right, and then I have some key, and in this case key would be the unique identifier, let's say the student number. Instead of searching my data structure, instead of looking for a good place for this particular key, what I am going to do is I'm going to push key through this h, hash function h, which is just going to mathematically calculate the appropriate index for this particular student number. And as you all know, if the table is implemented as an array, that essentially gives me random access. In other words, I can immediately go to that location in the table. I will not need to search the table at all. So, if we can design such a function that will determine appropriate, acceptable indices for the various keys, then what do you think would be the complexity of the search? On the first slide in this lecture, I've shown you that generally the data structures that we dealt with offered us the best efficiency of log n. What is the efficiency in this case in terms of the big O notation? Well, if we do not have to search at all, that means the efficiency is basically constant. It's a single step, it's a single operation. You take your key, that must be numeric or interpretable as numeric. You calculate the function h, the hash function on that key, and the output of the function is essentially the index, and you can go straight there. There is no searching involved, in fact. Thus, the search complexity boils down to just the complexity of the hash function. And if your hash function is efficient to compute, even if it's not very efficient, it's still just a single operation that has to be performed. And that is obviously quite amazing. I'm sure you can see that this is a lot more efficient than having to search through the various different values before you actually find the key that you need. So bottom line is, this is the holy grail of efficiency. We officially cannot do any better than constant. Constant efficiency is the ultimate best. It's mathematically impossible to create anything more efficient than this. Okay, so in this lecture we'll talk about what a hash function, how do you design a hash function, what can a hash function even be. And before we go into specific examples, let's think about what properties a hash function must have. First of all, it must be easy to compute. Yes, it's a single operation, but if this operation is something very complex that maybe also takes a while to compute, then obviously that would defeat the purpose. So we want hash functions to be very simple mathematical calculations. And then, of course, we want every single key to be hashed, in other words, to be given an index that doesn't clash with any other key. So if I have two unique students and my hash function gives me the same index for the two students, that would essentially mean that my two students have collided, and then I need to create some kind of a mechanism to resolve that collision, and it adds overhead. Or here's another example. Let's say I'm hashing various names into a table, and let's suppose my hash function for the name James gives me the index of 2, and that's fine. There is nobody there yet, so I can just put James into the index of 2. But let's suppose my hash function is designed in such a way that it only considers the first two letters of the name. It discards the rest of the text. James and Jane share the first two letters. So if I only use the first two letters to compute the index in the table, then James and Jane will actually point to the very same location in the table, and that is called a hash table collision. In the next lecture, we are actually going to talk about collision resolution, so there are algorithms to help you deal with this when it happens, but generally, we obviously want to design a function that creates as few collisions as possible. If we can create a unique index for every single unique key, that would be ideal. Here is another visual representation of a hash table, just to hopefully help the concept sink in. Essentially, a hash table is a data structure that uses hash functions for the indexing, and it's represented as this associative kind of an array. So every single key is not really stored, as is inside of our array. Instead, we have this hash function in between our hash table, or also sometimes referred to as the hash map, and the keys. And the hash function determines what index is actually used for every single key. Buckets in this case simply refers to the slots inside of the hash table or the hash map. So in this example, clearly for the various names, we want to store various telephone numbers, right? And then we will use the hash function to determine where the various telephone numbers go for the various people in our telephone book. Okay, so just to summarize, hash table basically maps the keys to values, to locations inside of a hash table. And we are going to use a hash function to compute these indices. So now that you know what a hash function is, let's talk about the properties of a good hash function. As we have already discussed, a hash function must be very easy to compute. It must be very efficient, otherwise you are obviously losing your time. And the second property, which is very, very important, is that a hash function should never favor any index over any other index. So if you have a table with a range of indices from 0 to 100, then any single index in that range between a 0 and 100 should be generated with the same probability. So we do not want a hash function that constantly only outputs a 10 for all the various keys and never goes beyond that or something like that. We basically want as evenly distributed indices as possible. And I'm sure you see why. This is just to avoid collisions. So yeah, generally collisions are not great, and if we manage to design a hash function that does in fact generate a unique hash value for every single key, such a function would be referred to as a perfect hash function. So this example that I keep using is in fact an example of a perfect hash function, because every single name that I'm trying to hash into my hash table does generate a unique index. As you can see, I do not have any clashes, I do not have any conflicts. One can go a step further and design a hash function that is not only perfect, but that is also minimal. So in the first example on the left-hand side, I didn't have clashes, but the gray blocks in between the blue blocks are basically the empty spots inside of my table that are not occupied by data yet. And perhaps they will never be occupied by data if I never manage to generate those indices. So with minimal perfect hashing, you don't only avoid collisions, you also make sure that not a single slot is wasted inside of your hash table. Designing minimal perfect hash functions is a lot harder than designing perfect hash functions. But there are ways to do this for limited sets of data, and in the last lecture for this week, so in the Thursday lecture, we will actually discuss one example of algorithmically designing a minimal perfect hash. Okay, so hopefully you get a good grasp on what a hash function is, at least theoretically. Let's try to make it more practical and less theoretical. Let's do some real-world examples. Let's suppose you want to design a hash function for phone numbers. So you have a whole bunch of customers that come to your company, and you know phone numbers are unique, so you decide to identify them by their unique phone numbers. Now, how exactly are we going to create this magical hash? First of all, let's ask ourselves, are phone numbers numeric? Well, they're made out of numbers, so technically you can interpret every number as you can interpret every phone number as just a number, as a mathematical number that you can do mathematical operations on. So let's be very primitive about it, very naive. Let's say, how about we use the phone numbers themselves as indices in the table? Will that make a perfect hash function? Well, it will, since we know the whole idea of a phone number is that your phone number is unique, right? So every single phone number will, in fact, if you treat the phone number itself as an index, it's guaranteed to be a unique index. It's not much of a function, right? It's like a one-to-one function, y equals x. We are just using the phone number itself. We are not being very creative about it. But perhaps that's fine. What can possibly go wrong? Well, there is something that can go wrong. Yes, it's a perfect hash, but it's extremely far from being a minimal hash. Because if you think about a phone number, it's usually a pretty long number, right? It's 8 to 9 digits, I'm not sure, but it's multiple digits. So what implication does it have if you use that entire number as an index? First of all, it must always be inside of your array boundaries. So if your phone number can be made out of 9 nines, then how large do you think should your table be? If your number itself can be 9 digits long, then that basically determines the size of your table, and you might have to create a table that's physically capable storing millions of numbers, even though you know you will only have 100 customers. So clearly that is extremely wasteful. So quite often what we do with hash functions is we take this really, really wide range of numbers and we try to narrow it down to a smaller range. And there are multiple ways of doing that. In the next few slides we'll discuss a couple of ways of doing it, but here are just some examples that might come straight to your head. Let's say we agree that the phone number is too long. Well, perhaps then we can use some parts of the phone number. What if we use the first 3 digits? We can do that, but that is an extremely bad idea, because if you have ever used a phone, you will know that the first 3 digits typically correspond to some general area code. For example, every phone number in Pretoria will start with 012. Every phone number in Johannesburg will start with 011. And 079 is, I don't know, a Vodacom cell phone number. 082 is also a common starting 3 digits for a cell phone number. So basically, if we decide to use the first 3 digits, we will have a huge amount of clashes, and that is definitely not a perfect hash. It's in fact a very, very bad hash. So if we can't use the entire number, if we can't use the first 3 digits, what if we use the last 3 digits instead? Well, that's a little bit better, right? The last digits usually refer to a unique extension. And that definitely is a better hash function. Is it perfect? Well, technically, you can have a phone number in Pretoria and a phone number in Johannesburg that have different area codes, but that maybe have the same extensions. So it doesn't completely exclude the possibility of collisions, but it's already definitely a better option than just using the entire number or using the first 3 numbers. So neither of these are perfect, but at least, with the second one we're getting somewhere. And this already gives you a feel for why it's not that easy to design a good hash function, because it really, you have to think about, well, what exactly does your number represent? What part of it is unique? What part of it can I maybe use to somehow interpret it as a unique index or to convert it to a unique index? And then going back to this idea of the number of digits you pick determining the size, the range of your indices. If we decide to use the last 3 digits, again, what does that tell you about the size of your table? That probably means that you will have indices in the range from 0 to 999. So that means you will be able to store 1,000 unique different telephone numbers. And that range will, of course, depend on your application. You, as a user, would know, as a developer rather, would know how many slots should you allocate for this particular database table. So we're going to talk about various primitive hash functions in this lecture, and the first one is extraction, which is exactly what we have done with the telephone numbers. Extraction basically says, all right, if your key is numeric, but it's really, really long, then you don't want to use the entire key perhaps, but you can use some part of the key to represent its uniqueness, to interpret it as actually an index in a table. And then, of course, what part you extract will really depend on the application. So for the phone numbers, we have determined that the first 3 digits are a bad idea. What about student numbers? Well, it turns out for the student numbers, the first few digits are also a bad idea, because they typically encode the year in which you have registered for your degree, right? The year in which you started studying. So in this example, I have both student numbers starting from 15, which tells me that they have both registered in 2015. So if I decided to use the first 2 digits, or maybe even the first 3 digits, I will definitely have plenty of clashes. So using the last 3 digits or the last 4 digits, depending on how many I want to store on my table, that would be a lot more appropriate. There is definitely more uniqueness in the last values rather than the first values. So generally, if you are using extraction, try to pick the part of the key that is least likely to repeat, that is least likely to clash. This is obviously super simple to calculate. You simply chop off part of your value and the rest is used as the index in the table. So it's very efficient. which is really what we want. I have told you in the past, hash functions must be quick to compute. However, in this case, we are not using the entire unique value, right? We're just saying, well, we use the last 3 of the last 4, or the last 5 digits, depending on how many students I expect to have in this particular class or this particular university. And it's all good and well, but because I'm only using a part of the key, I'm definitely decreasing the overall variation. I'm not using the entire unique thing, so I'm more likely to have clashes. And again, just like with the phone numbers, what assumption are we making about the size of the hash table if we are only extracting the 3 digits? It means that the size of the entire hash table will not exceed 1,000 locations, right? Our indices are going to be in the range between 0 and 999. Another important function is division. This one is very, very useful, in fact. So let's say we know how many students we expect to take a particular class, and we say, well, generally there are about 300 to 500 people taking course 212, so let me create a hash table that has exactly 500 locations in it. So I can actually preset the size of the table before I start populating it to some value t. And that value t is something that I know is appropriate for my application. This is how many users I expect to store in my database. So if I know how many users I expect, how many items, how many keys I want to store, I already know that whatever the hash function generates, those indices must be in the range between 0 to t minus 1. Otherwise, it will be out of bounds. So if my key is numeric, or even if it's text, I interpret it as a number, because obviously I will have to if I want to do math on it. If my key k is numeric, then the simplest division hash is to take the key and to apply the modulus operator to it. Hopefully you know what the modulus operator does. You're second years, I'm sure you've used it before. Basically, it computes the remainder of the division, right? And what exactly does that imply in this case? Well, if we divide, using the modulus operator, the key by the size of the table, then it will essentially give us a value that is in the desired range. If we try to divide something by t and then the remainder of that division is outputted, obviously the remainder will be in the range between 0 and t minus 1, which is perfect. So applying the modulus operator immediately pushes our values to lie in the desired range. And this, in fact, just a simple modulus operator is already a sort of a hash function. Let's say this is my hash table. It has 10 slots. Indices are from 0 to 9. So the size of the table is 10. T is equal to 10. Therefore, my hash function is going to be take whatever key I'm trying to place and apply the modulus operation and basically divide it by 10, calculate the remainder. So let's try to place the numbers into the table. 33 mod 10, where is it going to land? Well, you know the remainder of that division is 3, so it's going to go for 3. 16 mod 10, where is that going to end up? 6, right? 10 is divisible by 10, but 6 is not, so 6 is my remainder. 26 mod 10, again, the remainder of this division is 7, so 27 is going to go to location 7. 25 mod 10, again, the remainder would be 5, so 5 is where 25 will end up. 18 mod 10, what's the remainder? It's 8, so you know that's where 18 is going. 1 mod 10, 1 is not divisible by 10, so 1 itself is the remainder. It's going to go to position 1. And for 72, the remainder is 2. Okay, so we have successfully placed all the values. As you can see, the values are not sorted in any way, and the ordering appears random. But at the same time, if I gave you 72 and I ask you, okay, find it in the table, all you need to do is mod it by 10, and it will immediately take you to the correct location in the table. So no searching is required. Mod 10 immediately takes you to the correct index in the table. Okay, so the size of the table is 10, and it's all good and well. In my particular cherry-picked example, you obviously saw there were no clashes. However, let's take a step back. Let's try to be more realistic. Let's say I actually tried to hash a whole bunch of values that ended in a 0. Let's say I wanted to store 10, 20, 30, 40, 50, 60, and 70 or something like that. What would happen then? Well, if all of my values end in a 0, that means they're all divisible by 10, right? So there would be no remainder. In other words, if I was trying to hash 10, 20, and 30, 50, 60, and 70, all of them would actually compete for the location 0 inside of my table. So that would basically end up with lots of collisions. If many of my values end in a 0, obviously all of them will compete for that location 0. And that is not very good, right? It's almost like too many numbers are divisible by 10. Maybe if I picked 100, then the same thing would happen. Generally, if you pick a number that is potentially, that many other numbers are potentially divisible by, this remainder approach might sort of backfire. And that is why we are going to do a little bit of simple math magic. We'll say, well, actually, to make the divisions less likely, it's best to use a prime number for your size t. So even if I know I expect 500 students, 500 is too much of a round number. It ends into zeros. There will be too many collisions, most likely, if I mod lots of keys by that size. So a wiser thing to do would be to pick the next closest available prime number, some prime number that is the closest to 500. I don't know, 513. I don't know if that number if it's prime, but there are actually tables of prime numbers that you can look up the correct appropriate table size for your addition. Bottom line, prime numbers are better than non-prime numbers as far as hash table size goes, just because they typically result in fewer collisions. And sometimes, if you still end up with many collisions, you might even consider combining two prime numbers, where t, which you pick as a prime number, is the size of your table, and then you pick another prime number, an even bigger one than t, such that you first take your key mod p, and then the remainder of the division by p is also modded by the size of the table. And this double mod by the two different prime numbers essentially ensures that the numbers are spread even more across the various indices. All of these tricks are there just to reduce the total number of collisions. Another interesting and simple hash function is known as folding. And again, the idea here is to increase variability and to try and use as much information contained in the unique key as possible. So with extraction, we only used a part of the key, right? First part, last part, or maybe some recombination of first, last, and middle. And, we didn't use the entire key. So what if we actually wanted to somehow use up the entire uniqueness? What we can do is we can split the key into parts and then somehow combine these parts into a smaller number. For example, you can just add the subparts. And then once you've squashed your large numeric key into a smaller numeric key, you can still apply division hashing on top of that to restrict the index to the desired range, to the desired table size range. So there are a couple of ways of doing folding. Shift folding is very simple. You take your student number or telephone number, whatever numeric key you have, you split it up into subparts. In this particular example, I split it into subsets of 2 each. I can also split it just halfway. I can have 1,535 plus 1,871. There are multiple ways to split it. It really depends on what magnitudes are you looking for to get in the end. And once I've split my number into multiple parts, all I'm going to do is just add them up together. So my student number 15351871 ends up represented by 139, which is obviously a much smaller value, and hopefully it combines the info that the student number actually contains. And the way to visualize it is you take your number, you slice it into these individual little cards, and then you stack them on top of each other. You just add them up to get the total. And then, of course, just to make sure this fits into my desired range, it's always a good idea to mod your calculation by the size of the table. Boundary folding is a little bit fancier. It's also a similar approach. We still want to split up the number, but here we will say that every second or every third number inside of our splits will actually be reversed. So first we split everything up in a similar way. Then in this case, every second one, we actually transpose the two numbers. So 35 becomes 53, 71 becomes 17. And again, I also could have done it for first instead of second. I could have kept 35 and 71 and swapped 15 and 18 instead if I thought that would somehow add more variation to my hash. And again, if you want to visualize it, it's like you slice it up into these individual sections and every second one is actually flipped. But the idea is still the same. You are trying to take this long numeric and combine it, somehow recombine it, compress it into a smaller numeric, which is hopefully still unique enough. And once again, typically after you do some mathematical calculation, to ensure your number is within bounds, you will still mod it by your size of the table, where t is typically a prime number. Another option is the mid-square function. And this one says that you take your key, so your student number, your telephone number, and you square it. And after you square it, you actually apply extraction. So first you square it just to make it larger, to hopefully add variation. And then you extract the midpoints. In this case, I extract the 3 middle digits of the result of the square. Is this better than just straight-on extraction? Well, it's better in the sense that when you calculate the square of the number, obviously it uses the entire number as its input. So the square of the number is still representative of the entire number. And then if I apply extraction to that square, then hopefully the 3 middle numbers do not refer to just the last few digits or the first few digits. Hopefully those 3 middle numbers are actually somehow representative of my entire key. And I mean, obviously there can still be clashes, but by doing first the square and then the extraction on the square, I am actually reducing the likelihood of clashes. So this increases the variability of the indices that I would generate this way. So the advantage of mid-square, of doing extraction on mid-square versus straight-on extraction, is that this way I kind of try to recombine it in some way, and hopefully the mid-square is still representative of the entire key and not just its subset. So this is just a selection of functions. Remember that there is no one correct way of doing hashing. Generally, you can be creative with hashing. You should always look at your application at hand, and also you should remember that the various hash functions can in fact be combined. You can always first do the mid-square, then do some folding, then do the division on top of it all. All of these functions, all these hash functions can be stacked on top of one another if you know that would help variation. It's also beneficial to work on bit strings rather than numbers, because doing mathematical operations such as, for example, squaring a number is just a single binary shift to the right, which is simpler than actually performing the mathematical operation on integers or doubles. So working on binary level is generally more efficient. Yet another option is a radix transformation, and for this particular hash function, the idea is to take your key and to convert it to another numeric base. So let's say we have decimal keys. We can say, well, decimal is too much. Let's scale it down. Let's convert it to octal. Let's go to a numeric base of 8, which actually gives us slightly less variation in the digits, because we want to scale down from very large values to smaller values perhaps. And then after you've converted your number from one base to another base, you can simply apply division hashing to squash the number to the appropriate range. So again, student numbers, these are obviously decimal. I can convert them to octal, and this is how they would look in the base 8 numerical system. I can then apply my prime number, my table size, as a modules operation just to squeeze this into the appropriate range. And this can increase variation, although in my opinion, irregular transformations are a bit of a debatable topic. Because generally, so what happens in this case is you convert something to the octal base, right? But then you still treat it as if it was decimal when you're doing the modulus. And in this case, we actually have less variation on the digits. So I don't really see how this would help. I guess maybe if you went from octal to decimal, that will increase variation. Or if you went from decimal to hexadecimal, then once again, that can increase variation. But then how would you interpret the H's and the D's? As numbers, maybe you can substitute it with ASCII values. So it's definitely something to consider if you're out of other options. But in my opinion, this is not a very obvious hash function. But still, so that you know, this is one thing that you can potentially do. And this, again, doesn't guarantee that there will be no collisions, because if you take, for example, in this case, two decimal numbers, 2560 and 2048, if you take these two decimal numbers, you convert them both to octal, you will end up with 5,000 and 4,000. And these are obviously numbers with lots of zeros, so they are more likely to end up with some collision after you apply your modulus operation to it. Okay, so hash functions are really not that complex. I feel that when the idea is introduced for the first time, it might be kind of mind-boggling. You know, how do you avoid searching? How do you just know where to go in the table? And then when you think about the uniqueness of the keys and how each key itself can be kind of its own index, it starts to make sense. But still, if you have to somehow compress this long, unique value into a smaller value, I'm sure you would see that collisions might still happen at some point. So generally, applying a single hashing function is almost guaranteed to end up in some collisions, especially if you have a lot of data that you are trying to squeeze into a small kind of table. So if you know your table won't have many empty slots, the fuller it becomes, the more likely you are to start experiencing collisions. So can we somehow alleviate it? And yes, we are going to talk about collision resolution, but since this lecture is just about the hash functions themselves, let's talk about a way to delay collisions, to prevent collisions as far as we can. So if a single function is going to be likely to generate collisions, then perhaps we shouldn't use just a single function. Perhaps for a set of keys, we should somehow create a set of different hash functions that these keys can choose from, such that the variation is increased and thus collisions are decreased. So we want to define a family of functions where somehow every key does get some kind of a unique or semi-unique hash function all for its own. And you can actually, essentially a family of universal hash functions is such a family where for any two keys the probability of choosing the same index is equal to 1 divided by t, which is the size of the table, and the larger your table size is, the lower this probability will be. Such a set of functions will be called a universal set of hash functions. So let's just look at a couple of universal hash function families. Here is a very, very simple one. So we will say that we do not want a single h function, a single hash function h. We rather want to parameterize the hash function by two variables a and b. So every single key will get a hash function parameterized by a and b, and the function itself is very simple. You take the key, you multiply it by the a, you add b to it, then you apply the modulus operation with some large prime, and then you apply another modulus operation with the size of the table. And to make this universal, to really have this low risk of collision, what we are going to do is we are actually going to pick A and B randomly. So every single key will randomly pick a value for A and a value for B. And of course, if A and B are random, then essentially every single key will kind of have its own hash function that is different. And so if every single key is multiplied by a different A and a different B is added to it, then hopefully there will be a lower chance of collision at the end of the day. And if you were following the story, if you were following the plot of this lecture, you might stop me now and say, hold on, if A and B are chosen randomly, then how will I be able to find the key at a later stage? Because the whole point of the hash function is it's very deterministic, right? You have a key, you know exactly what math to perform on that key to get the exact index in the table. And now if we have these two unknowns, the unknown A and the unknown B, then how exactly am I even going to figure it out again? Well, okay, I placed it once by randomly generating A and B, but if I want to generate the same index again, how do I make sure I generate the same A and B? If A and B are truly random numbers, am I not shooting myself in the foot right now? And well, the solution is to add some deterministic factor to how you generate the random numbers. And I think the simple solution to this, hopefully you guys are familiar with random number generators and you know what the seed of a random number sequence is. A seed is basically a value that kind of starts up the pseudo-random number sequence, and every seed is going to generate a different sequence of numbers. So what if I use the key itself as a seed for the random number generator? So before I generate A and B, I say, okay, take this random number generator, seed it with K, and take the first two random numbers that it spits out. And if I want to find the same index again, the second time for this particular key, I can once again use the key as the seed, and that will guarantee that every single key, being its own seed, will always be able to recreate the same A and B over and over and over again in a deterministic fashion. So it's a trade-off between randomness and determinism, and this will definitely add a lot of variability to your hashes. We can also treat K as a sequence. So even if it's a student number, it's a sequence of digits, right? So technically, we can go ahead and multiply every digit by some randomly generated factor A, and perhaps just sum those numbers together. So this is a little bit like a folding. When you take your key, you split it up into subparts, and every single part then gets its own parameter by which it's multiplied before the values are added. And if this parameter is once again randomly generated, then hopefully enough variation will be added by this introduced randomness. This is also easy to visualize for strings, for example. If I'm trying to hash a piece of text, then every single character can be seen as a single value in the sequence, right? And then every single value in the sequence can be multiplied by some random value and added together. So for C, A, and T, I can simply use the ASCII codes, which are numeric. I can then multiply each ASCII code by these three random numbers, add all of them together, and then this summation is going to be modded by P as well as T to squeeze it into the correct range. And again, if I want 4, 7, and 2 to be deterministic given a key, I can once again use the key as a seed to the random number generator, and then random number generator seeded by the key will always give me random numbers, but they will be essentially bound to each particular key. Every particular key will have its own random number sequence. So since we mentioned strings, let's quickly talk about strings. Strings are obviously not numbers, so they are not as obvious to hash as the student numbers, for example. So how are we going to deal with strings in this scenario? How are we going to put strings into hash tables? The obvious solution is to use ASCII codes. Generally, if you are dealing with a key that is not numeric, you know you can only hash it if you somehow make it numeric, right? So for strings, like I said, ASCII codes work. Let's say I have my two strings, rose and soar. Clearly I'm trying to be difficult here. Both of these words are the same length and they're actually using the same characters. So they are quite similar, but I know in the English language they have completely different meanings. So clearly they shouldn't clash, right? So these are two different words. Again, let's say these are the ASCII values for the various characters. Now that I have the ASCII values, I can see that the ASCII values are actually, the same, but the order of the ASCII values is different. What I can then do is just concatenate the ASCII codes, for example, generating something like a student number, this nice long number, right? And then you mod it by t, size of the table, and you get your index. And in this case, because I concatenate them, they actually are still unique, because by concatenating the ASCII values, you actually preserve the uniqueness of every single string. And I think this is also a good illustration of why, in some cases, certain operations, certain hash functions are better than others. So concatenation clearly preserves uniqueness, while if I decided to add the ASCII values together, I would actually have ended up with a collision, because I know the ASCII values are the same. On the other hand, if rose and soar were using the universal function family, where every single item in the addition would have been multiplied by a unique parameter, then maybe unique parameters of rose, unique parameters of soar would have actually added up with different sums. So there are multiple ways to do this. But yeah, ASCII code is definitely one way. You can do something even more efficient than this. You can just say, well, it doesn't matter if it's string, if it's double, it doesn't matter what the data type is. At the end of the day, it is all binary. So what if I just take the binary string, which corresponds to this particular word, this particular sentence, and then instead of interpreting it as a sentence or a word, I actually interpret it as an integer. So I kind of implicitly convert it to the integer rather than a string. And then that integer can be, because it's going to be numeric, I can then suddenly apply all of the various math functions to it.